You will see my screen. Okay, in the last week there was a question for fatigue calculation, and that was related to silicon parts. And I must say, in the meantime, the majority of students in this lecture is not from microsystems engineering, and therefore maybe it's better to take another example. And I designed such an example, and imagine we have some part which has a microspring. So that's a small mechanical part, and the spring is always operated. Yeah, and springs are very frequent in all type of relays or uh, in parts which, for instance, do some fixture or such a thing. And for instance, when I was a glider pilot, uh, there was a mechanical coupling to the rope which was tying the glider up. And when you wanted to get free with your glider from the towing aircraft, you had to open that clutch, and in that clutch is a spring which keeps it shut normally, and so that clutch is operated, and after, let's say, 1,000 operations, you have to exchange that spring, because when the spring is operated all of the time, it is subjected to fatigue, and it's not a good situation when you're still hanging behind another aircraft, uh, because it's much easier to land when you're not connected using a rope of, let's say, 25 meter in between. So a spring can be safety relevant. And in our case here, um, we said we have a certain steel. That steel has a Baskin curve or a Wöhler curve in figure 214 in the lecture notes. But I also gave the number of um, cycles to failure um, for that material. And in fact, the Wöhler curve is described by, for instance, 770 megapascal. You have 200,000 cycles to failure. At 710 megapascal, you have 250,000. At 660 megapascal, you have 300,000. At 620 megapascal, you have 900,000. And now going to 610 megapascal, we have 3 times 10 to the power of 8. And at 550 megapascal, we have no failure at all. So how can we describe that curve? Go. Oh, sorry. So we can say that Baskin curve could also be a question to show it to me. So here we have the sigma. In the real Baskin, it's the logarithm of sigma. In Wöhler, it is linear plot. And here we have the log of cycles to failure. And that somehow goes this way here. And here we have the fatigue limit. And that's typically around 10 to the power of 6 to 10 to the power of 7 cycles. Okay, so that is a high strength steel, and also we see that is roughly 50% of the yield strength. So we have that curve. And now we have a so-called load collective that is a set of data which gives us for every stress amplitude, so the stress is and so on, and that is sigma A, and here is over time, and that gives us the number of cycles at a certain stress amplitude. And for instance, you would say I measure for a week or so, I do test measurements, and I get this set of data. So that means, of course, the number of cycles in each of these stress intervals. So here we could say, so it's always plus minus 20 or so in these stress intervals. We have a certain number of cycles which we measure. And of course, we could say here, how long did we measure? So we have here 1.05 times 10 to the power of plus so the total time is roughly 2 times 10 to the power of 7 cycles. And that's roughly, yeah, and that is roughly 1 hertz. So, and that's equivalent to 2 times 10 to the power of 7 seconds. That would be the test time. So divided by 3,600, and you get up something like what is it, 4,000 or so hours. So maybe half a year or roughly like that. And the question is, under these conditions, will the part fail? And when will it fail? And what will be the total number of cycles? So here we could say, when we take our data, we can see 1, 2, 3, 4 data that are here. Another data set is here. And one data set is here. So what we can see is clearly that is the fatigue curve, and that's the fatigue limit. Anyway, there is still a failure. And now the question is, what is uh, the total number of cycles when it will fail? And here we calculate a damage according to Palmgren minor rule. And here we can say, okay, here it's zero point 0.2 times 10 to the power of 5, so it's 10%. Again, it's 10%. Here it is 5%. Here it is 5%. And here it is, what is it? 3%. As cycles of failure is infinity, of course, we can say here that's 0%. So at that load, theoretically, because it's under the fatigue limit, we could test until infinity. So let's first sum up the damage. That's 25%, 30%, 33%. When will the sample fail? Do you have an idea? Now, what will yeah? Yes. Okay, that's simple here. We have 3 load cycles, at least in theory, and that means we have 2 times 10 to the power of 7 cycles. And that's roughly 6 times 10 to the power of 7 cycles, or 6 times 10 to the power of 7 seconds. So, okay, let me just compute how much it is in terms of hours, as we have 1 hertz. I just do my calculator, and that is roughly 17,000 hours. So in fact, it's 16,666. And how many um, days it is? So it's roughly 700 days, and that's roughly 2 years. Okay, so the spring would fail after 2 years, and in that way we had a very simple example of the Palmgren minor rule. Do you have an idea what is an advantage of Palmgren minor rule, and what are several, let's say, criticisms against that? Okay, good. Yeah. Um, okay. Uh, So it's ease of use, disadvantage. Um, Not precise. Yes, I also think that disadvantage is it is not really a physical model. Um, do you have an idea in the case of fatigue? What could be a physical modeling to model fatigue under variable conditions? What will kill a specimen? What killed the wheel ring of the ICE train? What was what was happening inside the material? Okay, okay, and that's the point. The crack was increasing, and let's say the increase of crack uh, per cycle depends on the load level. So in fact, physical model could be model crack growth. Yes. So the crack uh, grows from, let's say, from angstrom to micrometer, yeah, per cycle. So micrometer per cycle is something very severe. So that's rather low cycle fatigue. Angstrom is seems not so dangerous because 10 to the power of 10 angstrom is 1 meter. But anyway, when you think about something needing a crack of 1 millimeter, that's just 10 to the power of 7 cycles. Yeah. So that means crack growth is something important, and crack growth normally increases progressively with stress level. And in that way, one could also model uh, the behavior, because you could say, okay, I have several crack propagation rates, and I add them up finally until, yes, when a crack growth is given, when will the specimen fail? Um, yeah, okay, I agree. Yeah, that was correct. You have you have a crack growth, and when a critical intensity is given, so that means we have the stress times square root of length. That's the stress intensity. And if that exceeds a critical value, then the specimen will fail. It's not necessary that the crack goes through all of the material, but it's rather necessary that a critical state is reached where the specimen will fail. Okay, I think that was sufficient of uh, mechanics, and let's have a look at other example questions. Do you have questions with respect to this part? Ah, yes. maybe we can also say with a disadvantage. Some say sequence has an influence. So some say it makes a difference whether I first have low stress amplitudes and later on higher, or the other way around. The common opinion was that sometimes in materials you can have something like a training effect. So if you start with lower stress amplitudes, then later on also higher stress amplitudes can be tolerated in a better way. Um, then the failure criterion, just when the damage is larger than 100%, is it really correct, or could it be uh, something lower? Also here a safety factor is used. And another point is interaction with other uh, loads like climate. There is not so much knowledge about this. Um, we know that in certain conditions where we have additional chemical attack, we can have, for instance, hydrogen embrittlement, which is very dangerous. So that means if we have a steel, for instance, that would normally be we also ductile and have a high fracture toughness, would become brittle, and the fracture toughness would be degraded significantly. And in that way, cracks could propagate much easier. So that's something which is well known, but weaker interactions are not known so much. So that was a main reason why, in many cases, in former times, safety factor of 2 was used. Okay, now let's go back to the questions. Yeah, number 6 is also new. Um, Describe the concept of functional safety. What is the basic strategy? What are the relevant categories, classes for safety? What are relevant properties in these classes? Um, yeah. What is it, functional safety? Can you give me feedback? Um, First of all, maybe in order to in order to start, what is safety normally? How is safety defined? Yes, so we have the risk, um, and risk is something like in the FMEA, for instance, risk is severity times probability. Yeah, and here we have some limit here, or some boundary value, and here we are on the side of danger, and here we are on the side which is safe. Yeah, that's and that limit. Where do we get that limit? Okay. Yes. it's not really arbitrary. For instance, you could take a preceding technology and yeah, let's take an example. We go from mechanical control to computer control. Yeah, and so we already know where is what is risk in and what is a typical limit of such risk in conventional technology. And then we could first say, okay, for the new technology, we take the same maximum acceptable risk. Yes. Of course, when you introduce a new technology, you should at the same time reduce the maximum acceptable risk. Okay, that's a traditional way. But what is functional safety now? Here we have a different concept. So the traditional is risk is severity times probability. What is the risk in what is the risk in FMEA? Here we have a detection probability, or better, the inverse of the detection probability, and that means so we know if it fails, then the following can happen. The failure can be calculated as a probability. For instance, in our case of the mechanical spring, we can calculate the probability of failure after 2 years or such a thing. Yeah. Okay. On the other hand, we can introduce something which is a detection. So we have some indicator which says, okay, a failure cause is a failure cause is coming up, and that is, let's say, a red light for us that the hazard could come true, and in that way, the risk can be reduced. Yeah. So, for instance, what you could do is you could count the cycles. Yeah, you can take a sensor, for instance, like acceleration sensor on the aircraft wing, and that just counts the vibrations, or it can even do a classification saying we have that load collective after 1 month, 2 months, three. And in that way, we can, for instance, see if we approach the lifetime limit. Yeah, that would be some indicator reducing the risk, but that is not yet functional safety. What is functional safety now? And there is something which is really something in that concept is similar to that in the FMEA, and something is quite different, but it's one additional aspect. What is it in functional safety? O- Okay, that's same. Yes. Okay, that's always. you have the two criteria, severity and probability. Okay, I agree. You have that in functional safety, you have that in traditional safety, and you have that in FMEA also. Yeah? Okay, you always have these parameters. But still, in the functional safety, there is one thing which is really different. So imagine in a steer-by-wiring system, yeah, in a steer-by-wire system. So you have a steering wheel no longer mechanically coupled to your front wheels of your car, but only electronically. Uh, has ever someone done of you such arcade game where you have a racing game? Did someone do it? You put in a coin and then you can start racing. You see on the screen how you go along the track, and suddenly you run out of money. What happens then? Then your game just shuts off, and normally in that game you have some force feedback steering wheel. It turns off and you can easily turn on the wheel and nothing happens. Yeah, so game is over. Now imagine that would happen when you're driving at 160 kilometers per hour on the Autobahn. Not such a pleasant situation for you. But what is the requirement to functional safety? It includes it, but yes, but what is the basic concept behind it now? So now you're in your system you have for controlling your car just electronically. Something fails. Uh, what is a requirement to functional safety? Um, the concept of functional safety, does it, what is the primary hypothesis? Is it that something can fail, or is it that nothing will fail ever? Okay, and then, yeah, okay, that's a point. Yes, but to say it more precisely, you must bring it into a safe state. Yeah. So you have a failure, and you bring it in a safe state. Of course, it also takes a time to detect the failure and for the system to react. And also here, I would expect that such a system could only be accomplished by redundancy. Yeah. So you would have something like hot redundancy. Of course, you cannot have simultaneous steering with two such control systems. So one fails, the second must jump in immediately, and then the car is in a safe state. In that situation, maybe it should be mandatory what? To go to the workshop immediately or shut down the car? What would you think? I would think in such situation, maybe you should immediately uh, roll to the side and stop it, because when such a failure occurs in the second uh, part of your redundant system, then you will be in a situation which can no longer be treated or dealt with. Okay, that means we have a safe state. So, the probability to come into a safe state, how is it measured? Do you know how it is called? Do you have an idea? So in our lecture notes and generally it's called the safe failure fraction. And the safe failure fraction depends on your SIL level. So what is a SIL level? Yeah, and what is it? Mhm. Okay, the safety integrity level is a level of safety in a system that can deal also with situations that can uh, have a high danger, let's say it that way. So they could happen with a high probability and they could have a high severity. And if your system is able to deal with such situations, which could be frequent and or severe, and if the system is able to deal with such situations in a way that the system failure will have a low probability, then you have a high system integrity level. Um, what is one of the main strategies to get a high system integrity level? That is redundancy. And a second part which is required for good safety integrity is a high safe failure fraction. So that means, first of all, in a high safety integrity level, the uh, the probability that it will happen is low, achieved by technical matters. But on the other hand, the probability that when something goes wrong, that you will be able to deal with it, uh, then this probability must also be high. Of course, the probabilities are not, let's say, not too excessively high, but they are quite high because already the probability that the failure event will happen should be already quite low. Yeah, but these are two main parameters. One is a probability, and in the safety integrity, you can also discern between yes, between continuous operation or, on the other hand, operation on demand. That means only when a system is used from time to time. Okay, so please have a look at it. But what I would like to say is the following: the functional safety concept. The main thing is uh, when the failure or fault has happened, the system must deal with it. In the FMEA, it's the other way around. The detectability, which is something like a probability of failure cause detection. Yeah, that is a thing. So uh, that also should be kept in mind in FMEA. Um, the severity is the measuring the effect of a failure. The probability is the probability of the failure itself, and the detection probability is the detection probability of the failure cause. Yes? So you could say in FMAA, they look at before it happens. In functional safety, you look at it after it happens. Also in FMEA, you have a chain of events, but time is nothing which is really a parameter here. But in functional safety, of course, time is important because you have a certain time in which your system must react. Yeah. Okay. Driving at 160, you have not so many seconds, yeah, before the system must be back in action again. Okay. So also one thing, so like to uh, I would like to highlight a question which always will come. Um, you build a complex system. It's also in the lecture notes, and insulin dosage system. Or would you also prefer something like an aircraft? What will we take as an example now? Aircraft or medical system? Okay. Um, I'm always quite astonished how many students don't know about an aircraft. Everybody is coming from India and China to Germany, and from Germany to Spain and where else. And yeah, how does an aircraft work? So here we come back to the lecture name is reliability engineering. Yeah, so we must know how an aircraft works. What is the main effect of an aircraft? Yeah, Bernoulli equation, and so here. Yeah, so it has also a drag, yes, that component, and lift. So a good aircraft has low drag and high lift because the relation between uh, lift and drag determines what the gliding ratio is. Yeah. Okay. So, um, what do you need for that to work out? What is the main parameter that keeps the aircraft flying? So the aircraft is going that direction, and that's a vector. What kind of vector is it? Yes. let's make it shorter. Also, it's a speed, yeah, velocity. Uh, which velocity is it compared when you measure velocity, you always think it's against something. Something is stationary. So, against what do you measure velocity? Against ground? Yes, that's important. Okay. What will happen when airspeed is too low? Yes, lift. Yes, stall is perfect. Stall. Why is it so? When you have an aircraft and you fly slower, let's say when that's the line here, you can just make it steeper and steeper. And the more you, yes, increase that angle against the air, the higher is your lift. That was the main invention of a very famous, let's say, pioneer of aviation, of Otto Lilienthal. He found that behavior, but he also found that when the angle is too high, that's the stall angle, yes? And that angle is also associated with the stall speed, yeah? So you get slower and you always increase the angle and you still will fly. But at a certain angle, you have no longer that airflow here, but you have only turbulences. Yeah, and that means the aircraft will really stall. Okay, what is when speed is high? What will happen when? Yeah, imagine you build a paper airplane. Yeah, and now you take it in the hand, you throw it. Okay, it will work, but now you take it in a car and hold it out of the window. What will happen to your paper airplane? Yes, the force too high, it will disintegrate in some way. Yes, so that's a more noble term for rupture or break. Or, okay, okay. Um, so what is the main parameter? That is speed. What is the most important sensor in an aircraft? Yeah. So normally when I do not start that way with first discussing about how an aircraft works, then in most cases I do not get the answer that it is a speed sensor. And when I started in that way to discuss about the wing, and so also often, yes, I also see that it's not possible to derive that in a stringent way. Okay, good, fine here. Um, why is yes? So now let's go to Pitot tube. Uh, what is it? Yeah, how does it work? Yeah, yeah. Yes. Yes, all forces, yes, is proportional to speed square. That's something which is very important. And yes, total pressure. Okay, still in that way, density has to be compensated. Um, okay, two openings. Now, what's the problem with pitot tubes? Hmm? So you fly in a sandstorm, yeah. Some years ago, I don't know whether you remember, there was volcanic action in Iceland, and so there was a lot of dust in the air, and so flying was not permitted for a week or so. You still remember that? Yes. I was in Sweden for 3 more days than I had hoped for. Uh, ice. Um, what what are uh, what are possibilities to make your system more safe? Hmm. How could you do that? Yeah, that could be, but there is one disadvantage. Yes, yes. Um, that is one thing which is important. At least one could use GPS for in order to check whether the measurement of the pitot tube is reasonable. Yes, that could be something uh, you do. Um, yes, maybe not a pitot tube, but another kind of pressure measurement could be used here. But imagine we would have no redundancy. Yes, when we look at the concept of functional safety, what could we do with a pitot tube? It also would not work against both of these phenomena, but against one. What could we do? Hmm? Heating. So you could say that's some kind of functional safety concept. You heat it either all of the time or you heat it when you think conditions are of icing. Yeah. Okay. Um, how do you call that that type of failure when icing or blocking occurs? It's a typical. It's a killer of redundancy. Yes, and but something special. Environmental cause. It's a common cause. Yes, and it can lead to common failure mode or common mode failure. That means all sensors are iced, for instance. Yeah. Now imagine you would build a pitot tube with, yes, in some way you must measure pressure. In former times it was just, and still it is done in aircraft in a just mechanical way. But you would have an electronic system. Yeah, what would be, let's say, three basic elements of your sensing system you have? What do you need? You have the pitot tube. So here you measure pressure, yeah. What else do you have? How do you measure pressure? Yes. So it's a sensor. And what else do you have? Yeah, okay. Let's say instrumentation, including computer control. So it's electronics. So in that way, that might be one thing. You could also say, okay, I also have a display, for instance. Some indicator, and now you have such a system. You want to know what can go wrong, and also you want to know how probable is it in that system that something goes wrong. What can you do? So you're in a company like, let's say, LITEF, for instance, is such a company. There are many more of these. Such a company designs such sensor systems for aircraft. And now you go to the aviation agency and say, okay, I want clearance to build it and sell it. So what do they require from you? What is the most important part they want to see? And again, as I said, in fact, you and they want to know what can happen and how probable is it. How do you call that analysis? Also, it's part of the complete functional safety concept. So that's almost all of the techniques we have used in our lecture here are belonging to that set of analysis. What is a set called? So it's a risk analysis. And for the risk analysis, what kind of analysis do we have? We can group it in several ways, but for me it would first be sufficient if you just name some. Okay. What else? And or what? Where do we use and or? Sorry? Yes, fault tree analysis. Um, if you do not model the failure but the function, what can you do then? Reliability block diagram. Um, okay, we know what it is. That is the so-called inductive. In fact, bottom up. It's not quite correct. Why? The failure propagation is bottom up, but the system structure is also made top down, yes? But it's classified as a inductive. These are deductive analysis. And what else do we have? Okay. Yes, Markov is written with V or double F, or depending on uh, whether it's English or German language. Uh, Here you model probabilities over time. When we have transitions. What else do we have? What is the most simple analysis? If you take your fingers, 1, 2, 3, 4 also. Yes. So it's just the sum of all lambda e. And what's the parts stress? What is that? It's again lambda e, for instance, as a function of Ti, yes, for individual conditions. Each part is stressed in its own way, and therefore we take the respective failure rate. And for individual elements, that is not in the lecture notes here, but it is important. It's a physical modeling. So Wöhler, Raskin, Coffin-Manson, Arrhenius, and so on. So the physical modeling is rather used on an individual element, and from that then you can go into part stress, And so we have most of the methods we have seen in that lecture. Yes, the okay. Now, when we have come to that point, it could be that I would like to see you explain to me FMEA. What is important in FMEA? So there could be questions concerning what is a team. Second is 5 steps. And third is, what is it? RPN, risk priority number, how to determine. Okay, so as these methods here uh, are the most important methods in reliability engineering, you should be familiar with these methods. Yes, so that is something which is very important, that you know about these. Another thing is also the physical modeling, also what the terms reliability, failure rate, failure density, failure function, and so on mean. Okay, that's also important. And now imagine you have done a risk analysis and what are the requirements you get your product into the market? So you go to the authority and yes, what are the requirements? So in the end, you get clearance to sell your pitot tube speed sensor system. Is every company allowed to build such systems? What are requirements to produce? What is normally in almost all products in the meantime a requirement you can come into the market? A requirement to your company. Hmm. Heard about quality management system? So that's important for the company. Then you must have a risk analysis and a risk management plan. And that's more or less same in automotive industry, in medical industry. And you also must have prototypes tested. And what is also important, when you are in the production phase. So that could be also in the design, qualification of the product. That is relating to the company. And what is relevant for production? Yes. And conformity. That means your product is that you produce is more or less the same like the prototype and the design. Uh, Also, that means uh, you cannot just change anything. Even when things go wrong, what do you have to go do then? For instance, you are in production selling, you know now you have a safety hazard. What do you have to do? So you produce your parts, your sensor systems, you sell them to Airbus, to Boeing, to uh, Lockheed, and whom else. And now you find out, yes, the failure rate is 50 times higher than you expected. What do you have to do then? Some would go on producing and say maybe we can repair them later or such a thing. Is that allowed? No, it is not. You in such industries, you must stop. You must warn the customer. You must seek for the failure cause or the fault cause, and then you found the cause of the fault. What will you do then? Do you have an idea? What is your opinion? So you found it. So again, it depends on, of course, what happened. For instance, if the failure rate is just high, then because you had some fabrication defect, then maybe you just eliminate the source of this, and then you can say, okay, I'm back to standard situation again. I go on producing. But uh, imagine you had a misdesign. Yeah. For instance, you find out um, the processor overheats, and that's the reason why the system goes in a faulty state. And now you redesign your printed wiring board, you give it a cooling system. You also change a little the programming so that the processor load is not so high. And then what is, can you then just go back to production? Yes, not only you have to go to the qualification, yeah, depending on how severe the change is you have done. Also, that is a reason why I do not really believe in the strategy that in cars you can just uh, incrementally improve the software, for instance, for autonomous driving. Yes, because when you do a change, that change might affect also other things than what you just wanted to repair. That means, in fact, you need a new risk analysis when you do a change of your system. And yeah, that's that strategy of risk analysis, risk management, prototypes tested. On the other hand, uh, production, quality control, making sure that in the production phase the product is identical to the qualified product, and only in a quality management system that is industry real, industry typical. So the medical industry has other quality management system than aircraft industry. Also in Germany, for instance, in aircraft you need uh, to be a so-called LTB, which is Luftfahrttechnischer Betrieb. Otherwise, you are not allowed to do any technical work on aircraft. And in that way, there are strategies to make products safe. Okay. From my side, I think I'm through with what I wanted to teach, but maybe we have some time still today. Do you have questions to me? No questions? Okay, then I would say I I would finish for this semester. In case you have any questions, you can still address me. Best is always you send me an email. Um, okay, in the last two sessions, you also should have noticed what probably the style of exam would be. So the style typically will be start with something and then on that example go through all of the, or not all, but some of the risk analysis and going to through some of the strategies we have derived here. And in that way, I think you can prepare yourself. Okay, then thanks for your attention. Maybe another point. I got no feedback for this lecture. Uh, Maybe you have some feedback you would like to give to me here and now. What could be improved, for instance? What was good or bad from your point of view? Mm, mm, yeah. Yeah, uh, that is correct. Um, Sometimes, yeah, in most years I do it the other way around. Sometimes the problem is that I do not finish all of the stuff I wanted to teach. Also, in this semester, I introduced more or better things like this functional safety or this. I improved this part on the mechatronic system design, and so I wanted to be sure I would cover all of that. Another point from my side is that generally the kind of exam is yes going over all of it. Yes, I also think there are some aspects which should be known well. So I always in the in between I I said all of these basic mathematical functions, for instance, are also important, and also uh, I came back to these several times because I thought that of course it is very important for the understanding of the further uh, lecture part. Okay. Um, yeah, sometimes I think maybe it could be more than 2 hours, maybe 3 or 4 even. Um, on the other hand, there are also other lecturers which give insights into reliability, resilience, and so on. For instance, in the INATEC, yes, they also have very good uh, lectures there. Some even go deeper or go to adjacent fields. So from my side, this is just, let's say, uh, an insight into the basic technologies. On the other hand, from the experience of work in that field, uh, I think it is important, first of all, to see what are important technologies. The second thing is, I was in Daimler Company, and my boss at that time, he came from another university, and he was involved also in reliability and mainly dependability and so on. And he made some for the complete Daimler Corporation, he made a big seminar. Maybe we were, I don't know, 150 persons in that field. And the first thing was that these high-ranked managers and so on were asked, what do you understand by reliability? Uh, and my yes, what I found out was that maybe 2 or 3% of these were able to describe the term reliability correctly, yeah, in terms of a technical description like we have used it in this lecture, or on the other hand, going from reliability to safety and so on. So that was astonishing me very much in a company like Daimler, which claimed to produce the safest cars in the world. Yes, and so that was one of the reasons why I thought it would be good to have such a lecture just to explain the basic concepts of reliability and also safety engineering. I hope I succeeded in some way. Okay, no more comments? Then we can stop uh, for this year and this semester, and I see you in a few weeks. Okay,